Greetings, everyone. Welcome to this webinar. I'm Sylvia Rissel, Senior Variation Engineer at 3DCS. Today, Tom and I are going to be talking about doing a model of a gear mechanism, and we're going to talk about the interactions between the teeth and how you can use this kind of modeling to improve your process and your product. And of course, here we are. We're going to be talking about gear design and the GD&T and the assembly and the contact. Tom's going to run a really great demo for you and talk about the results and some additional capabilities for the 3DCS Variation Analyst software. All right, so last gear webinar we were talking about specifically modeling the interaction of a single tooth along the axis between the two pivots and how it interacted with the inside of the two teeth on the other gear. So one gear tooth contacting two other gear teeth. And working with those faces, we can measure angle backlash between the two gears, or in fact in the whole gear train, and axial backlash. We can also measure pressure angle and do a flank test and understand where the contact is between these two surfaces. All right, so if you design perfect gears, perfect involute, everything exact like CAD is, we can set up perfect meshing, a constant distance between the gear centers as things rotate, and no clearance between the gears. Unfortunately, in reality, the mounting of the gears, the shafts, the bearings may not be perfectly aligned. They won't have the exact center that the CAD does, and you have the risk of having teeth interfere and might cause the gear to lock or wear or put forces in other parts of the assembly that you don't want. Some common ways of dealing with this problem are moving the gear centers apart, so the nominal distance is a little bit more than you'd expect from the mathematically perfect involutes you created. This has some problems with stress and efficiency. You might also have some tip interference, and there's ways of dealing with that. Another countermeasure to improve your gear life is to crown the curve the surfaces of the gears to make sure that your surfaces contact near the center of the tooth rather than over here at the edge. Another common way of making sure that your gear trains work all the time is to effectively remove the surface and make the teeth thinner. You're removing material that's a stress, and so that weakens the teeth a little bit. All right, now we've been talking about the digital twin. Simulated testing of your CAD, your digital twin of the parts you're going to create, is going to allow you to test early in the design process and possibly do a couple of iterations of your design before creating those physical prototypes. So 3DCS will allow you to do a Monte Carlo simulation of your gear assembly and evaluate the performance of your design before anybody cuts any metal or molds plastic or whatever. All right, the 3DCS simulation you're going to see is going to use this gear. Datum A is the surface, datum B is the hole in the middle, and datum C is there just to identify the orientation of the gear. Most significantly, we've got a profile of 0.06 on all the teeth, and this bore here has perpendicularity diameter of 0.1 back to A. So it's a little bit misaligned to the surface, and we have some profile on all the teeth. All right, the simulation that Tom is going to show you is that of a gear roll gauge. So we've got the work gear that has all that GD&T applied to it, and we have a master gear that is perfect CAD. So we're going to be moving the gears so they mesh, and moving them together so the teeth contact each other. This is intended to measure radial composite deviation, and in a real world test of this, you test a bunch of these gears and do multiple tests on them, and your measurement of center to center distance will determine whether they meet your quality requirements. You need to do the full rotation and measure this for the full rotation. A little bit more gear details. This is set up for a 0.15 millimeter backlash. We've got a crown modeled on these. All right, so Monte Carlo analysis is going to advance the gears 1 degree at a time over 30 degrees because 30 degrees is 1 tooth rotation. So 360 divided by 12 teeth. And we have these teeth assigned a random variation. So each build we simulate with Monte Carlo is going to have slightly different tooth profile. All right, now's the point where we hand this over to Tom because he's going to show you this demo.
Oh, thank you, Sylvia. That was very clear. I hope I can stay as clear as you do. My name is Tom. My name is Tom Ogens, and I'm a senior dimensional analyst, and I have a corporation called CATIA Integration, and they do work for DCS. And one of the things we were working on is this gear module, and I'm going to demonstrate some variations of the gear module and show how this relates to the webinar, to the presentation of how to do a test gauge. So here's my screen. And one of the things that you can do with 3DCS is they have an option called an add-on, mechanical, and with that you can design a system so you have rotation in sequence, gear by gear. And each rotation is set up to show the contact. The contact is this square dot in the center here. So as it rotates around, we get it in the right view. You can see it, the dot moves along the edge as the tooth rotates. And up to now, we've been doing one tooth in one position, kind of at one of these dots, and varying everything else. Now in this webinar, we're going to rotate the gears, and it's actually going to switch to another tooth. So you can see it's right at the tip here of the tooth on the gear on the left, and now it's switched to the top. And this is in nominal position. And what DCS does is it puts all of the GD&T that we've described in the gear and adds that to the gear rotations, and does a variance on the angle. So the angle also is a variable, and that gives us a complete simulation of the tooth-to-tooth rotation. This is a way to view it, and also it's in the paper where you can look at all of the measurements in sequence and get some insight as to what happens as the gear rotates. So the module we're using is called the gear module. It's right here, and that was discussed at a previous webinar. And the output in this demonstration is from the gear module with some additions. So I'm using model variants in this, which allows me to quickly change the setup and show different things. So the thing I want to demonstrate now is the GD&T. So this is a representation that's used by DCS to show the GD&T locations. The A datum is the flat, which is shown here, and the B datum is the bore, the center hole, and the C datum is the clocking point. Now the B datum has a perpendicularity associated that Sylvia showed. Let me bring that up. Now, when you want to see what's happening with GD&T, you have to show the mesh. So let me turn on the mesh and zoom in on the B datum here. And you have something called visualize effect. So if you hit visualize effect, and we probably want to put some delay in it here, you can see that the mesh is rotating, but the part stays the same. So the mesh is going back and forth, simulating the Monte Carlo simulation of the perpendicularity of datum B to datum A. And this is a handy feature. Sometimes you increase the amount just to make sure it's doing the right thing. Let me close this one. Now the other interesting one is the tooth. So let's look at the middle tooth here. And look at, and there's the 0.06 millimeter. And zoom in on it a little bit. And look at visualize effect. And you can see the tooth, all faces of the tooth are moving at the same time, and that's because they're grouped together. Each tooth is separately toleranced, but they're all, within the tooth, they're all grouped together, and that gives us the Monte Carlo simulation we're looking for. Now, in order to bring the full effect, we have to bring in the bearing. So let me show a bearing here. Now this has not moved has not been aligned to the gear, as you can see. Let me just turn off the gear for a second. So in the bearing, datum A is actually on this side of the bearing. So if we go to the bearing and the GD&T, that's datum A, and datum B is the shaft hole, not the outer hole. That way we can tolerance the outer shaft and the flat independently of the datums. And if you have a real bearing, this bearing is a perfect bearing, but if you had a real bearing, you'd want to make the shaft perpendicular to the flat, the outer shaft here. the outer bearing race, perpendicular to A with the tolerance, and that would add the realism to the bearing. You can also make the outer race positional to the B datum, and that'll make it act like a real bearing. So that's very important to set up A and B as the gear and bearing properly. Now let me go through and turn on the tolerance gear again. And also, this is displaying the different variants. So this is the move to B. So now if I hit nominal build, they should move together. You see they're aligned together. And now when we do what's a deviation of it, simulating the deviation, you can see the gear is moving because the order of move is to move the gear bore into the outer race of the bearing first. So let me pause this.
So we're seeing each random build is keeping the bearing stationary and move each time you do a random build, the gear is ending up in a slightly different place.
That's correct. Yes, and also are the teeth. So the teeth are moving and the gear is moving as well. So the way this works is the gear bore is moved to the bearing surface. So now we're not really, the GD&T order is not really affecting this. That's just to put in the tolerances, but the moves are separate. And then the flat is moved to the other flat, and there's an offset because the bearing is offset from the flat. So if you set it up right, then this works very well. If you change the setup, then you really have to understand what the effects of every change is. So this is a recommended way to set up all the gears, including bevel gears. You need to have a flat and set it up this way, even spherical bevel gears. The next thing we're going to look at is the flank test. Flank test is a visual check to see how the gears are contacting. And this allows us to make sure they're contacting in the center and not at the tips in the wrong part of the rotation. Yeah, this is done by running the gear module and then using deviation with a sweep. And what the sweep does is it keeps all the points up there. So it's going to add points as we go, and you'll be able to see the points there. You can see this one just added to the tip here. And then they're going to continue to add points, and you can see the contact pattern. Now, it's somewhat better to view it as a shaded. And we can watch the points go there. So the flank test has all of the movements in it, but then it moves it back to the original position so you can watch it. So first it goes through the deviations and contacts, then it splits apart into the original deviations. And you can see some of the movement of the gear on the right from the variation. And also you'll notice it's not attached to the bearing because it moves off the bearing for us to view it. And
can you rotate it a little bit because it's kind of shadowing the surfaces that we're looking at.
Okay. Yeah, so let me see. It's always better to pause. So you can see the pattern there. Oh, okay. Now before we rotate it some more, I can put the pattern on the other side. And now And now the, let's see if I pause it. Now you can see the points are starting to show on the other side. Now let me turn it back to wireframe. And now you can see the points, but it's hard to see. It's harder to see the surfaces. If I use wireframe with hidden line, now it's a little bit clearer what's happening. So you can rotate it around and see both sides. So you let this run, and it runs for a while, and you can come back and check it and make sure that the patterns there's a standard pattern that's for the set of gears that they're expecting, and make sure the standard pattern matches. Now, one of the things you might be concerned about is this one at the tip, this point at the tip. That's right at the tip of the gears. So you want to make sure that that's not where the gear is putting the most force. And so that would be a concern with this particular gear set. Well, this is our run analysis demo, where I'm going to demonstrate how to find the min and max values so you can actually look at them. So this is the run analysis screen that comes up, and we're going to look at axial backlash. This is the nominal position that you usually start with. But if you hit this button here called show min, it's going to rotate to the minimum position, and you can find out the angle and any other measurements that are there. And in some cases, you can create a new measurement and find out a new measurement because you found something interesting.
So this is the minimum axial backlash that we're looking for.
Yes. This is the minimum value that came up, and you can see that the gear rotated from where it was to here, and that you can now look at the different measurements. So one of the measurements that is interesting is what's the rotation angle. So this is 9.46 degrees. So you could set up the analysis by changing this move from a rotation of the entire process, the entire gear span, into 9.46, and then it'll rotate there, stay there, and then you can get accurate contributors of what's going on at that point. And you can actually look at any other measurement. So you could look at let's say you want to look at the angle backlash at that point. So you can find out what the angle backlash is, and at that exact point. And then if you look at angle backlash, you might find that they're correlated. So let me bring up you can do the same thing with the maximum and get the correlation to the maximum. So this is a very powerful tool. There's also a way to find any particular value of axial backlash and find out the position of the gears and what the other measurements are. And if you're looking for something specific, this is a very useful device. That was our demo. And now let me go over some of the fine points in a slide presentation. So what we've created here is essentially a virtual gauge where we can look at the gear positions, the contributors, the histograms, and contacts of various measurements. And we can summarize them and look at how they compare to our specifications. So we've been looking at axial backlash, the nominal value, the minimal value, and the maximum value. As you saw in the demo, the contributors and the measurements are all available. After you make a run, you can go through the whole scenario. And these are the angles that the angle backlash that we had. Let me go through the next slide here. So here are the contributors. Here's the positions of the gears in the two degrees. This is the minimum and this is the maximum. And you can see in the minimum, tooth 10 is not a contributor. And in the maximum, tooth 8 is not a contributor. And you can find out which teeth are the contributors and what are the rotation angles. And in DCS, it comes in the form of this report, which was translated into this report. So you can look at that, and they also have a graph so you can quickly find out what's contributing to the variation in this particular measurement. One of the measurements is the single pitch deviation, and that's the value of the true or the nominal tooth to the actual position of the tooth as you compare one tooth to the other tooth. And this is a measurement that's very important for gears, and it can be done in our DCS as an add-on measurement. It's not part of the gear module. The tooth angle backlash, which is part of the gear module, for this example where we have two gears, it's the amount of angle between the two gears near the contact points. And this is standard DCS. It's another way to say it is the rotational angle traversed when the gear is rotated from one contact point on one side, the drive side, to the reverse side.
So that's pretty quickly available with the 3DCS gear module?
Absolutely, comes right with the gear module, same as axial backlash. And another measurement that's important is the pressure angle. When the gears contact, one of the vectors coming from the contact is in the tangent to the drive gear. And that's the force that's actually pushing on the other gear to make it rotate. And the other direction is tangent to the normal. And the angle between them is called the pressure angle. So the pressure, the tangent vectors are what's driving the gears. The pressure, the other vector, is pushing the gears apart and attaching force to the bearings and bearings force to the housing or to the axles, to the housings, and pressurizing the whole system. And until those equalize, a lot of the force is used to pressurize the gear system. Once they equalize, then the pressure from the teeth transmit to each other very efficiently. So if you have too much force, it's going to break something. That's why bearings wear out, or the housing screws come out of the housing, other things happen. So the pressure angle is a very important gear measurement. And we talked about the flank test and this tooth tip issue. And after it runs for a while, you get this kind of pattern, which allows you to compare the results to the specifications. Okay, so I think that's all we got for the presentation.